We were discussing about the expand operation. In the last class, we saw an example of expanding cubes in cubes of a given Boolean function using espresso minimizer. So essentially, we are looking at blocking matrix and how the blocking matrix ensures that the expanded cubes are valid and they are not intersecting with the offset of the function. So this is the example that we saw, and we saw expanding a cube w bar x y z bar, and then we saw how to fill this blocking matrix where the columns correspond to the cubes of the offset and rows correspond to the variables of the cube that we are trying to expand. So it is a covering problem. So pick the fewest rows that cover all columns, and the expanded cube is the product of those rows. And we saw this, the expanded cube for w bar x, y, z bar is either w bar x or w bar z bar. And blocking matrix guarantees no expanded parts of your cube intersects with offset. So pick the rows or variables that cover the columns. Keeping the variable keeps the expanded cube from ever hitting the offset. And when you add the variables, the single product term, that is the bigger cube, you get also does not hit any of the cubes in offset. So in the current example, if we choose the solution as w bar x, then this is what we saw. W bar keeps it from hitting the offset cubes of these offset cubes, and x keeps it from hitting the offset cubes denoted by these pink, offset cube set. Okay. So we will consider another example which is slightly different from the first one. We will not form the blocking matrix, but we will see it is very similar to that. We individually check the validity of expanded cube. So from the positional cube notation perspective, suppose the given function is f is equal to a bar b bar c bar plus a b bar c bar plus a bar b c bar plus a bar b bar c, which is on f on the onset, and fdc is a b c bar. So if I write there are 4 cubes in the onset, I write them in the using the positional cube notation, though they are these, and then you find the column sum that becomes 3 1 3 1 3 1. The offset is computed using unit recursive paradigm, so you know the onset and you know the FDC DC set, so you can always find the offset. Offset is if you find the offset, it is 0 1 1 1 0 1 and 1 1 0 1 0 1, that is AC plus BC, and FDC is this. Now if you multiply this with the transposed version of this last column count, you get the implicant weights as 9 7 7 7. Now the smallest weight is 7. So you choose second cube to expand first. Now let us. So all of them, if you see, have 3 variable or 3 literals in that. So apparently it looks you can choose any of them for expansion. But if I use this method to choose the first cube or the best cube to expand, it is a second cube. Second cube, let us take second cube for expansion. Second cube is 0 1, that is a b bar c bar 0 1 1 0 1 0. Okay, this 0 1 1 0 1 0. And now try raising the variables from left to right. So I have to now, make this cube bigger. That is, we are trying to make it prime. So how do you do that? We can actually 0, 1, this is A. I have to drop A. How do I drop A? I make this a don't care, or I may erase this variable A to from 0, 1 to 1, 1. Okay. So erasing 0 in the column 1, that is this column, we get 1, 1, 1, 0, 1, 0. That is B bar, C bar. So B bar, C bar is the raised cube or expanded cube. Now we have to see whether it intersects with the offset. Now you know the offset. Offset is here 0, 1, 1, 1, 0, 1 and 1, 1, 0, 1, 0, 1. So we will try to find bitwise AND operation of this expanded cube with the offset. So 0, 1, this is offset 0, 1, 1, 1, 0, 1. Bitwise ANDed with 1, 1, 1, 0, 1, 0. That is this expanded cube. So I get 0, 1, 1, 0 and the 0, 0. The last column becomes 0, 0. So that is void. Similarly, the second cube in the offset is 1, 1, 0, 1, 0, 1, which is bitwise ANDed with our expanded cube 1, 1, 1, 0, 1, 0. So that also gives you a result which is void, which means the expanded cube does not intersect with the offset. So this expansion is therefore valid. So this does not intersect with the offset. This expansion is valid. Now, then what we can do is, you see, we still have this is B bar, C bar. We can raise B bar to to I don't care. That is, we can make 1, 1, 1, 1, 1, 0. That is only C bar. The B bar, C bar cube is expanded to make it C bar by raising this 0 to 1. Okay, so that is our next step. Raising 0 in column 4 gives 1, 1, 1, 1, 1, 0, which again does not intersect with the offset. You can see, even if you make this 1, 1 here, you have a void and the third column. So in this third variable column, you still have a void. So even if your B bar is expanded, B bar, C bar is expanded to just C bar, even then that does not intersect with the offset. Okay, so even after doing this, which again does not intersect with the offset, and hence the expanded cube, that is 1, 1, 1, 1, 1, 0, which is just C bar, is valid. Now, finally, if you raise the 0 in the sixth column, that is this column, 0 in the sixth column, we get 1, 1, 1, 1, 1, 1, which obviously intersects with the offset. And this expansion is therefore not valid. So when we raise this to 1, 1 as well as this to 1, 1, the C bar to 1, 1, then this will interact with this offset. So therefore that expansion is not valid. Okay. So therefore the expanded cube, that is 0, 1, 1, 0, 1, 0, that is A, B bar, C bar, is expanded to just C bar. Okay. So, but we can also see that just C bar covers the first and third cubes of original onset. You see, if you look at the original onset, that is this. We have started with this expansion of this, and we have expanded this to just C bar. Then C bar encloses A bar, B bar, C bar, as well as A bar, B, C bar. Okay, both of them, all these three will be covered just in C bar. So I need not again expand A bar, B, C bar and A bar, B bar, C bar, because they are already covered in this C bar, which is the expanded cube of A, B bar, C bar. Okay. Now, therefore, the next cube to be expanded is only A bar, B bar, C. Okay. So that is what is given here. So this expanded cube covers the first and third cubes of original F1. So no need to try to expand first and third cube. Now take the last cube for expansion, that is A bar, B bar C, okay, the last cube. Raising zeros in second or fourth column would intersect with the offset and hence cannot be raised. So you make this 1, 1, then you see offset is here. Okay, if I make this thing as 1, 1, then that will intersect with this as well as this. Similarly, fourth column, 1, 0. If I make it 1, 1, then also it intersects with the offset. Okay. Second or fourth column. Second or fourth column would intersect with the offset and hence cannot be raised. Raising 0 in the fifth column, this column, will not result in an intersection with the offset. Okay. So you see, suppose I raise only the fifth. So I will probably I will write here. So what is our this thing? Original cube for expansion, that is expand 1, 0, 1, 0, 1, 0, and offset is what is our offset? Our offset is we'll just 0, 1, 1, 1, 0, 1. 0, 1, 1, 1, 0, 1, and 1, 1. What is the offset? 1, 1, 0, 1, 0, 1. 1, 1. 1, 1, 0, 1. 0, 1. Now you raise it's small. We are trying to expand this 1, 0, 1, 0, 0, 1. Okay, 0. And see whether so if I expand this, if I raise this 0 to 1, this will hit the offset. That is, intersection of this with this will hit the offset. Similarly, intersection of by raising this to 1 also will intersect with the offset. You can see that by doing bitwise AND operation. On the other hand, if I expand only this, okay, so that is if I try 1, 0, 1, 0, 1, 1, and you see a bitwise AND operation with this, which gives you this is the first one is void for this. Okay, the intersection of first two this with the intersection of this with the first cube of offset gives you void. Intersection of this with the second cube also gives you void because this is 1, 0, this is 0, 1. Okay, similarly here 1, 0, 0, 1, so it gives you offset. So this is a valid valid expansion. Valid expansion. Okay. So therefore, raising 0 in fifth column will not result in an intersection with the offset and hence valid. The expanded cube of 1, 0, 1, 0, 0, 1 is therefore 1, 0, 1, 0, 1, 1. Hence the prime cover of the function is 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. So these are the only two cubes that are left. So this is essentially which is equal to this together is our C bar plus A bar B bar. This is our prime cover for the given function. Is this clear? Yeah, reduce operation transforms a cover into a non-prime cover with the same cardinality. Okay, so prime into a non-prime. Okay, it is just the opposite of expand operation. The reduce operator attempts to replace each implicant with another that is contained in it, subjected to the condition that the reduced cube along with the remaining cubes still cover the function. Okay, so we will see. So this example, if you see, this was our original cover with the 4 cubes. After reduction, you get something like this. This is not the only possible way of reduce operation. You can club, you can reduce to a different cover also. But the only thing that you need to remember during reduce operation is to have the same cardinality. Okay, here it was 4. Here also you should have 4. You cannot reduce, so that each what is that? Vertex, onset vertex is a separate minterm. Okay, it is not that. The cardinality should remain same. So, what is the input to the reduce operation? Cube list F that covers function F. What is the output? Cube list that covers F with each implicant reduced. Maybe not prime, some may be prime, some may not be prime. Okay, so that no implicants overlap on any minterms. Okay, so there is no overlap. If you look at here, after reduction, there is no overlap. Okay, whereas here there is overlap, here there is overlap. After reduction, you don't have any overlap. So let us see an example. So strategies for each cube C in F. Now from heavy to light. See, now I have to reduce the cubes. That is, prime should be made non-prime. So I should look at cubes which are biggest. Okay. So intersect C with the rest of the cover of function F. Remove from C the minterms covered elsewhere and find the biggest cube that covers the reduced C. Replace C with this reduced cube. So here is an example. Suppose you have this this is a Karnaugh map. This is a function represented by the Karnaugh map, and let us denote these cubes. These are all prime implicants. This is alpha. This is along the. This is alpha. This is beta. This is gamma, and you have delta. So my onset vertex onset or F1 onset function is alpha, beta, gamma, delta. Let us say we want to reduce alpha. So I have to reduce alpha. So what I need to do is you find the set Q, which is F minus alpha. Okay. How do I reduce this? I find Q is equal to F minus alpha, that is beta, gamma, and delta. So remove alpha from the cover F. Okay, you are left with the beta, gamma, delta. Then find Q bar. See, when you remove alpha from alpha, beta, gamma, delta, you are left with beta, gamma, delta. That is this, and this. That is our Q. Find Q bar. When you find Q bar, what you get? Everything other than beta, gamma, delta. Find Q bar. And then find alpha intersection Q bar. Okay. Then alpha intersection Q bar is only this term. That is alpha tilde. That is the reduced cube alpha. Okay. Similarly, you can reduce delta in the same way. Remove delta from the function F. That gives you Q. Okay. Then find the complement of Q, which is complement of this F minus delta bar, and find the intersection of delta with the this Q bar. So that gives you reduced delta. So similar to alpha. So that is how you do. So basic trick is pick a cube and remove it from your current cover of F. Carefully intersect it with the complement of the rest of this cover. Minterms in this intersection are what you want to keep. Repeat on next cube. So let alpha with the cube to be reduced. Find q is equal to f minus alpha. Intersect alpha with the complement of q. Okay, alpha intersection q bar gives you this. That is what you get the reduced alpha. Super cube of the minterms in this intersection gives you the reduced cube. So the same thing, just illustration. So you have picked alpha to reduce. Okay. Now find the complement of this is when the q that you have obtained is f minus alpha. Its complement is this. Okay. Complement is this. And now intersect alpha with this complement. Okay. You will get reduced cube alpha tilde. Okay. Any questions? Are there any questions? Yes. Okay. If there are no questions, we will continue. So express operation reduce. The basic strategy is weight cubes like expand plus. So I have to find the weight of the cubes. But now process the cubes from heavy to light. That is, last time we were trying to expand the non-prime into prime. Now we are trying to reduce from prime to non-prime. Therefore, I have to consider the biggest cube. Heavy cube covers lots of minterms. So better chances for reduction of heavy cubes first. Process cubes one at a time in this heavy to light order. So what does reduce do? Starts with a prime cover and shrinks individual primes in it. You still get a cover of the function, but it is probably not prime anymore. Idea, this is a good starting point to do expand again to regrow cubes in a different direction. So why do we do the reduce operation? Because after reduce operation, you see here, after reduce operation, this is reduced alpha. Okay, this is reduced delta. Now I can expand this alpha in the downward direction to make it prime. Okay, so these four, and further and reduce this and expand in this direction. So you will be left with only three cubes. This beta and one that is covering these four minterms and one covering this, that is delta. So delta, and then this expanded alpha, second time expanded, and then this beta gives you the irredundant set of prime cubes of F. So that is the idea. Okay. So here is an example, very quick example, that F is equal to this. Okay, 1 1 1 1 1 0. That is, this is C bar. So that is this function, this cube, and alpha and beta. There are only two cubes in the function F. I want to reduce them. Then I have beta. Beta is A bar B bar. A bar B bar. So now I find the column sum. It is 2 1 2 1 2 1. I multiply this with the 2 1 2 1 2 1. That is the transposed version of this, and you get the weights as 8 and 7. So I have to now reduce a cube whose weight is maximum, because that is the bigger cube. So alpha is heavy because its weight is 8. So beta is light. So I have to so choose alpha to reduce. Now how to reduce? So find a function q which is f minus alpha. So f minus alpha is actually beta, because you have only alpha and beta in f. So if I remove alpha, you get only beta. Therefore q bar is beta bar. I have to find the complement of this q bar, which is beta bar, which is beta bar. So this is alpha. Okay. Now this is beta. What is beta bar? Beta bar is these six, you know, six midterms in this region. Okay. But there actually beta bar is, I have to consider one this and another this, which is one this. Okay. Yes, one this and then this. That is B and A. So beta bar is A and B. Now you intersect alpha with the beta bar, that is Q bar. You get two cubes. Alpha is one cube. Now we intersect with the two cubes of Q bar. So you get two cubes of intersection of alpha with the beta bar. But now alpha should be replaced by two cubes, which is not what we wanted. Cardinality should remain same. We wanted to reduce alpha with one single cube. Okay. Reduce operation should not increase the cardinality. Here the cardinality has increased because you get two cubes. So alpha cannot be reduced. Okay. Now try to reduce beta. So you find Q which is F minus beta, which is alpha. Q bar is alpha bar. What is alpha bar? This is alpha. Alpha bar is this C. Okay. Alpha bar is C. Beta intersection Q bar, which is beta intersection alpha bar, is this intersection with this. Okay. This intersection with this is this one single cube. That is A bar, B bar, C. Okay. So if I reduce this function, I can only reduce the cube beta. So reduce beta to get this. Okay. So alpha remains same. So this is our reduced cover of the given function. So you still have only two cubes in and the reduced function. So the cardinality has not changed. Cardinality still remains same, whereas it is the reduced this thing. Okay. So here is another example. You have this. You try to reduce. Now this is not a good reduce operation because after reduce I have to do expand operation to get a better cover. So if I expand this, I don't, I may end up with the same this thing or something even worse. Whereas if I reduce this into this, okay, this is another option because you have 4 cubes here, you have 4 cubes here. Now this reduce operation, this resultant solution after reduce operation is better because now if I expand this cube with vertically, okay, you cover these two together so that you get an expanded or prime cover with only 3 cubes. If I expand this in the next step, when I expand this, you will be left with just 3 cubes in the cover. So a cover with the cardinality 4 is reduced to cover with cardinality 3 and it is prime and it is redundant. Okay, so that is the advantage. So this is a better reduced result compared to this. So that is reduce operation. So that comes to the end of the reduce this lecture. So if you have any quick questions, please go ahead. Are there any questions?
Sir, I had one question.
Yes.
So during this reduce operation, is there any way to directly come to the good structure of?
No, there is no way. You can't. It is a kind of trial and error actually. See, you reduce and then expand, hoping that the new expand operation will be different from what you originally started with.